Professor Longwell, Ken is a professor of high energy physics at Imperial College London and STFC. What is interesting is he's been working on transformative technologies for development and in radiation biology. But something different from all the talks we've heard this morning is that he's going to talk about his LhARA, which is a laser hybrid accelerator for radiological applications. So that's a new concept they haven't heard so far. So Ken, really looking forward to that. Thanks a lot. Floor is yours.
Okay, thank you very much, Manjit, and thanks for the opportunity to present our project here. So where to start? I decided to go back to the beginning, and Ugo Amaldi has already summarized all of this, of course. I think the key point that I wanted to make was that, of course, Wilson was working on the development of accelerators for scientific applications. He came out of working on the Manhattan Project and wanted to find a way of using radiation to the benefit of mankind as opposed to just blowing them up. So when he was working at Harvard, designing the 150 MeV cyclotron, he actually laid the foundations for the field. So Ugo already described how he was looking at the properties of ionizing radiation, contrasting what a proton could do with what photons would do. He also noted the benefit of carbon and made a number of calculations, presumably on paper and with a slide rule, looking at the range dependence of the beam with the proton energy, looking at that in terms of the energy loss. So this is now linear energy transfer, or the DDX of the particle. And he was already distinguishing between the Bragg peak, so the pristine Bragg peak in modern jargon, and a spread out Bragg peak, which is coming from the properties of the beam as well. So he really laid the foundations for the field way back in 1946. So this is the Livingston plot. It's really usually used by particle accelerator or people doing science at particle accelerators to demonstrate how rapidly the maximum energy of accelerators is going up. But I wanted to look at it from a different point of view. The first cyclotron, so Lawrence is credited with delivering the first cyclotron in 1932, first synchrotron in 1946. There was then a gap. What I meant to say was that the synchrotron and the cyclotron were used for biological studies pretty early in 1948, as you've already heard. So these are really scientific studies. There were treatments coming relatively early. Here, this is more to do with biochemistry or not really. It's not really treatment of cancer. The first treatment of cancer was out in 1974 at the Massachusetts General Hospital. And the gap here between the accelerator exploitation and the first delivery of beams for irradiation of tumors has to do with imaging, calculating the expected deposition of the radiation to make sure that you illuminate the tumor and not the healthy tissue. So really, the issue of taking novel accelerator technologies and delivering them for the benefit of radiation therapy has to do with the whole system. And I think that's a key message that I wanted to give, and it's a key thing that we're taking forward in the LhARA context. It's not good enough just to develop the beam. You really have to develop the whole system. Okay, so today, as we've heard, particle beam therapy has really developed into a sophisticated thing. Everybody has their favorite plot. This is an irradiation of a spine in a child, where you can see that the dose, the hotspot where the dose is in red, is really conformed to the spinal cord, which was the key thing that was wanted. This is done in facilities based on cyclotrons. So this is a shot of the facility which is operating in the Christie Hospital in Manchester. I picked that because it's local. And the point I want to make is only that the accelerator, so the cyclotron, is this little thing in the top left of the figure. And all of the rest of the facility has to do with beam transport and the gantry system. So really, the goal to reduce the footprint and the investment cost is really got to do with beam transport, the gantry, more than it has to do with making the accelerator small. Of course, to deliver the heavy ions, as you've heard, requires or usually is done with synchrotrons. So this is a screenshot of the Medostrom facility. So here the accelerator is somewhat larger, but the whole facility is still dominated by the beam delivery, and in particular for carbon ion gantries, the engineering feat and the size of that is really enormous. Okay, so that's where we are now. So I just wanted to look at the timeline. So the field started, if you want, in the 40s. The state of the art now is in synchrotron and cyclotron delivery of various ion species to patients. If we look forward to, say, 2050, what we really want to be doing is delivering radiation precisely. So we're really targeting, if not cells, then at least local volumes of tissue. We're getting rid of the distinction between the tumor volume and the target planning volume. I've probably got all the jargon wrong, but anyway, the various shells of the onion coming from uncertainties need to be reduced. And that's really what we're trying to do with the LhARA initiative. We're really trying to take the state of the art now, which is delivering great benefit in the treatment of cancer, to something which is highly precise and has can be exploited more widely by having a smaller footprint and has a greater throughput. And as I've emphasized, this has to do with not just the accelerator, but the system. Okay, so that's, if you like, the introduction. Now, what I wanted to go through rapidly was the challenges and opportunities. We've chosen to focus on the radiobiology for a demonstrator, which is LhARA. And that is really because the entry price is much lower, because the energies that we need to deliver are lower. So I'll describe the reasons why you would want to have a radiobiology program. Of course, I'll describe LhARA, and then I'll try and draw some conclusions. Okay, so challenges and opportunities. I think everybody here knows that the motivation for what we're doing is that cancer is the second most common cause of death across the world, and that radiotherapy, presently most often delivered with photons, is indicated in half of all cancer patients. There's a significant growth of demand predicted. So if you look at these numbers, you can see an enormous rate of increase from 2012, when these statistics were collected, to 2030, which was the projection in the paper I was looking at. Of course, you've got to remember that those surveys are carried out in places where there is treatment. So this is typically in the high income countries. If you look at the low and middle income countries, you can estimate the benefit you would get from being able to deliver radiotherapy across those places. And the estimates indicate that there's an enormous, so 27 million lives could be saved by 2035 if it was possible to provide the requisite provision of radiotherapy. So to meet the predicted need in high income countries, and moreover, to meet the need in low and middle income countries, you need an enormous scale up in provision. And that really requires one to think about the development of novel techniques. And those novel techniques have to be integrated in a cost-effective system so that you can make a distributed network of radiotherapy facilities. Okay, so just defining a few bits of jargon. We know about the Bragg peak. We know that the Bragg peak of a carbon ion is more localized or has a sharper cutoff than the proton. This is really to do with the fact the way that the energy transfer happens in the ionization process. Note that it has a tail here. This comes from fragmentation of both the target, meaning the carbon, oxygen, and other nuclei which are in tissue, and the projectile itself. And because the fragments are lighter than the projectile, so the carbon ion, you get a tail which comes at greater velocity and leaks out the back of the Bragg peak. So it's small, but it's still there. And by comparison, this is the photon equivalent. A key issue is the therapeutic window. So there's the tumor kill probability. So this in a cartoon way rises with dose. And then there's a normal tissue complication probability, which also rises with dose. And the therapeutic window is the degree to which you separate the killing of the tumor from the damage to healthy tissue. And the whole objective is to increase the therapeutic window. So radiotherapy is most often delivered with photons. It has an enormous beneficial effect. The difficulties with it is that the dose is delivered, the photons penetrate through the tissues such that they leave a maximum dose in a certain region after a certain distance traveling through the body, but then the dose continues through the patient, falling roughly exponentially with depth. And that means that the dose that you can deliver to the tumor is often limited by the proximity of sensitive organs or organs which are less tolerant to radiation. And of course, the use of particle beams, so proton and heavier ion beams, is there to try and minimize the damage to healthy tissue. Okay, so there is strong evidence for the benefit of proton over photon beams from the point of view of sparing of organs at risk. The carbon therapies, we believe, have other advantages, but the real evidence for, let's say, the clinical evidence for the benefit of carbon over proton is presently limited, and I think that's an issue that we want to be developing. I think the key thing is that with the heavier ion beams, there's evidence that you would have particular benefits for hard to treat tumors, and that those would increase the number of indications for which one could use the ion therapy, and that is the motivation for trying to develop those more difficult kind of facilities. We know that protons have superior dose deposition profile to protons. These cartoons for tumors in different regions of the body allow you to look at how much better, in principle, the delivery of carbon ion therapy would be. So the benefits of using the heavier ions is really coming from the degree to which the multiple scattering and DDX processes differ between the two particles. So I showed you the way in which the Bragg peak was had a sharper fall off for carbon ions than for protons. This is a simulation of the width of the beam, so the degree to which the beam is spread by multiple scattering, and you can see that there's much more precisely defined edges of the beam in the carbon ion case than there is in the proton case. And this means you are not illuminating, the beam is not spreading out as much as it travels through the patient, and you're illuminating less of the healthy tissue. There's a quantity called the radiobiological effectiveness. So this is the degree to which a particular endpoint is delivered using a particular dose of a particle beam compared to the same endpoint, so the amount of cell death that you would get using a photon beam, so an X-ray beam. The origin, so typically if you use proton beams, you have a 10 or so % increase in the relative biological effectiveness. For carbon ions, it can be very, very much greater, so perhaps a factor of 3. And the origin of this comes from the interactions in the tissue. So for 1 MeV protons in water, you see these places where significant ionization events are happening and electrons are being knocked out, and the proton is delivering energy to the tissue. You can see it's relatively sparse. It's even more sparse with photons. For carbon ions, you can see these events are really concentrated in a very, you have many such interactions per centimeter. And in fact, as the carbon is slowing down, the mean free path between collisions is really getting down to the size of the diameter of the double helix. So the damage to the DNA is really being caused by primary interactions, not by the free radicals. The balance between that needs to be understood better. There's another collateral benefit, which is that you can use those electrons which you're producing in order to do positron emission tomography inside the patient during the treatment. If you look at the benefit of carbon over protons from the point of view of the cell survival as a function of the physical dose, really the benefit of carbon is really coming from the difference between the dose that you deliver to get a particular survival fraction in the cells using protons versus carbon. And you can see that in principle, the heavier ions have a much better therapeutic effect than the protons alone would do. So that really motivates the need to look at ion species. We also understand the need to spare healthy tissue and therefore to look at precision in the way that we deliver that. And then we want to look at the degree to which there's, if you like, there's opportunity to change the way particle beam therapy is delivered in order to reach a larger population of people. So if you look at the statistics for where proton beam therapy exists in the world, there are of order 70 or so proton beam therapy facilities in operation or in operation, 40 under construction. So there's of order 100. If you look at the map, you can see these are typically in high income countries, and that's the origin of the lack of provision elsewhere. There's incremental development technique going on. Of course, the existing suppliers are developing their machines, and there are new initiatives such as NIMS and CINS, which are really trying to drive the provision of this kind of therapy forward. To meet the needs that I've outlined and to try and make a large set of distributed facilities, one really needs to be looking at novel technologies. So really one wants to take a transformational approach, or at least a set of investment should be invested in transformational approach, and that's really where we position LhARA. So that's about the delivery, spreading the delivery. I think we ought to look briefly at the indications that novel beam topologies are really having exciting indications of increasing the therapeutic window. So I'm going to do two worked examples. The first is flash, which has already been mentioned. Conventionally, if you're delivering proton therapy, you're doing it at the rate of order 2 grays per minute. The flash regime, there's discussion about what flash therapy really means for protons, but let's take the definition as being in excess of 40 gray per second. So you can see there's many orders of magnitude increase in the rate. What was observed first, so actually the history goes back a little bit further, but in 2014 there are papers which are being produced which shows that with flash radiotherapy the normal tissue damage is much reduced compared to conventional radiation. So this is using X-rays. A little bit later, after some studies in mini pig and cat, so 4 years after that publication, the first treatment was carried out in 2019 of a skin cancer, which was resistant to radiation. So I think my point here is that in this case, the high rate of radiation was able to preserve the tumor killing probability while reducing normal tissue damage and therefore increasing the therapeutic window. The other thing here to note is that the time difference or the opportunity to make a benefit to patients is actually relatively small, because the first observation published here is in 2014 and the first delivery was in 2019. So there's opportunity to make a difference. That's time domain, if you like. In the spatial domain, there's evidence that if you don't deliver the beam uniformly across the tumor, but you deliver it in small beamlets so that you have a gap with no radiation between places where you have intense radiation, you can get the same tumor kill probability, but again have normal tissue sparing. So in this mini or microbeam technique, what people have observed is that there is a significant increase in the resistance to collateral damage in healthy tissue, and that means that one is able to increase the amount of dose which is delivered to the tumor, increase the tumor kill probability while maintaining the same complication probability, and therefore increase the therapeutic window. So that's, if you like, indication that in the spatial domain, one should be studying what is the best technique to be looking at, to be delivering the radiotherapy in. Which is a motivation for looking at why we want to look at studying the fundamental radiobiology, which underpins the therapeutic effect of radiotherapy. So what I'm showing you here is the relative biological effectiveness. So it's defined is the effect of your radiation defined with respect to a reference proton beam. The data for in vitro and in vivo irradiations is shown on the right-hand side. What I'm showing you is, as a function of dose, the relative biological effectiveness for various studies. And I think my wish is to draw your attention to the scatter of the data and the size of the error bars. What is used in treatment planning is a value of 1.1, which definitely describes the data, but you can see that there is a large variation. Furthermore, it is known that the RBE depends on, well, it depends on the energy of the ion, it depends on the ion species, it depends on the dose and the dose rate, the tissue type and the biological endpoint. And the mechanisms by which the RBE is determined are not really known at a detailed level. Furthermore, if you look at the spread of data for ion beams, so what I'm showing you at the bottom right is a compilation of the RBEs as a function of the linear energy transfer, so DEDX, if you like, in keV per micron, for different ion types. And you can again see the spread of the data, and the value of 1.1 is used for protons, and an effective value sometimes of order 3 is used for carbon ions. And you can see the degree to which the uncertainties arise due to the spread of the data. So I think that to maximize the efficiency of particle beam therapy now and in the future, one really requires to be able to tie down the precision with which one can make predictions. And I think that making detailed measurements are an important part of that program. So a little bit more about how the physics of this is going. One can define radiation as being in a number of types. So you can have low LET radiation. Photons would be the avatar of a low linear energy transfer type of radiation. So here's a photon. Across some distance in the tissue, it's making a relatively small number of interactions. That typically makes radicals, which then cause damage to the DNA. Critical types of damage using double-strand breaks are believed to be important in killing the tumors. So if you did a high LET radiation by contrast, so carbon ions would be a clear version of this, as I tried to show you before. You get these primary ionization events, which are really now happening at a level which could disrupt the DNA in more than one place in a single passage. That makes multiple DNA pathways in the lesions of there are multiple pathways by which to create lesions in the DNA. That means that there's more difficult to do for the cell to repair, and it enhances the cell death. If you look at the plots on the right-hand side, you can see the degree to which you can measure a difference between low LET and high LET effectiveness of the radiation, and it really motivates delivering radiotherapy using higher LET radiation. However, you can see the quantity of the data and the size of the error bars, and really one needs to be looking at the dynamic study. So in other words, studying how this effect develops and what the time structure of the beam that you might want to have to make the maximum disruption. And I think one needs to be developing a program which is looking at how to interpret those results, perhaps using Monte Carlo codes such as G4DNA or Topaz NBio. Okay, so just a last piece of data. What I'm showing you here is that carbon is more effective in killing cancer stem cells than proton radiation. So what you're looking at is oh, half my labels have gone. This is a Mac feature, I think. Anyway, so if you look at the different doses that you're delivering and tumor volumes, you can see that there's a clear difference between. Let's stick to this one. The cell death, which is coming from carbon ions and using X-ray, so that you can see the benefits, which is coming from the delivery of radiotherapy using carbon ions. Okay, so what we want to do then, so this is, if you like, the motivation for LhARA, is we want to be studying the biological processes, so the biochemical, biological processes In the time domain, this is presently the focus is on flash, but perhaps there are other effects. In the space domain, there the avatar is on is presently in the mini and microbeam area. We also want to be looking at the ion species. We've data about the difference between protons and carbon. I think we want to be studying helium and other ions too. We clearly need to study the effects as a function of energy, and we need to do all of that in combination with other types of treatment, for example, chemotherapy and immunotherapy. And ideally, one would create a facility which at the research level is able to explore all of that space. To do that, we really need to have a multidisciplinary approach, because you can see that natural scientists like myself only know about a subset of the things which need to be known in order to optimize that facility. So what we've done is create the LhARA collaboration. I've just put the logos up here, but the key thing that I hope you take away from it is that we have created a collaboration which runs from clinicians, clinical oncologists, all the way to laser plasma physicists and particle physicists. And I think that's, if you like, the key thing that we need to take this program forward. Okay, so LhARA then. So what is LhARA? What we want to do is to take a novel, what we're calling a hybrid approach. So we want to take a high power pulse laser. We want to strike that into a target, a thin target of an appropriate form, which is then produces ions. So it's really the intense electric field which is inside the laser light, which is accelerating the ions. A key benefit, or we hope it's a benefit, is that we have a very short laser pulse, and that, so long as we produce the accelerator in an appropriate way, is able to deliver a pulse length in the ion beam, which is very short. And our estimations for LhARA is that we can deliver beams as short as 10 to 40 nanoseconds. Key thing is that the electric fields which are inside the laser are very, very large. And that means we can produce ions with energy significantly larger than you can produce in a conventional ion source. And I'll show you in a minute that our goal in LhARA is to capture at 250 times roughly a typical energy you can get from an ion source. We want to reduce the cost and increase the efficiency of the capture section. So we want to use novel plasma lens focusing. So here we want to create an electron gas with the right kind of electron density in order to provide a strong focusing system, but with a short length. And something which really you would have to have a conventional magnet that weighs several tons, or a superconducting magnet to be able to do in a clinical environment. We want to preserve the time structure of the beam. So we've chosen to use a fixed field accelerator, an FFA in the jargon, because we don't have to fill the magnets, and therefore we can accelerate very rapidly. I think I wanted to point out one more thing on this slide, which is that you get the beam a fixed time after you trigger the laser. So here, the repetition rate and the time structure of the beam that you will deliver is really determined by the amount of money you're willing to spend on the laser. We've specified 10 hertz because that controls the price of the laser. People are developing 150 hertz lasers as we speak. And I put up the drawing of this, which has the dimensions on, to claim that this is, well, I think it would be a unique facility if we could build it, but I think it would also be quite compact. Okay, so our vision, or our ambition, is that we're going to create this uniquely flexible novel system. It will deliver, so its scientific deliverable will be a systematic and definitive radiobiology program, but the technologies that we hope to build it with will prove the feasibility of the laser-driven hybrid accelerator approach. And in that way, we intend to lay the technological foundations for the transformation of particle beam therapy by developing LhARA into an automated patient-specific therapy system. So this will take till 2050 or 2040 maybe, and it relies on the online imaging, fast feedback and control. So it's the system elements that we want to be taking forward as part of the initiative as well. Okay, I think I said most of that, so I'll skip over it. Right, so a bit more detail about LhARA. So what we are intending to do is to use a 100 terawatt laser. So that delivers of order of a joule in 35 femtoseconds. and then that produces a spectrum of particles that I'm going to show you. We're going to capture somewhere over 10 MeV, so our baseline specification is at 15 MeV. And that allows us to overcome the space charge limit that is present at the injection of particles into the first accelerating structure in today's particle beam therapy facilities. We deliver very short pulses because of the time structure of the laser beam, and it's triggerable, as I tried to point out. The key feature of the plasma lens that we want to use is that it does not use a high field solenoid. And we want to be able to deliver variable energies of protons and ions without using a degrader, a solid degrader or a material degrader. So we really want to have variable extraction energy from the FFA. Specification we've adopted for LhARA is that we will be delivering protons in the energy range 15 to 127 MeV and ions with energies in the range 5 to 34 MeV per nucleon. Simulations based on GEONT have allowed us to estimate the performance. And what I'm showing you here is the dose rates that we think we can calculate. So remember that we use we've specified a 10 Hertz system. If you look at the average dose rate, you can see that we're able to provide beams where you can study the flash effect. The instantaneous dose rate, because of the short pulse rather than the number of protons, is enormous. Okay, so I'm just going to take you through the way in which the LhARA we hope will work. The production of the ions happens through a process that's called target normal sheath acceleration. So what we plan to do is to shoot the laser at 45 degrees onto a thin foil. So in a light beam, the electric fields are perpendicular to the direction of motion. So with the laser impinging at 45 degrees on the surface, we're having an electron beam we're having an electric field which is oscillating into and out of the plane of the foil. That accelerates the electrons, so it causes the electrons to accelerate in or out of the foil. Those that are accelerated into the foil ionize the material, so it creates more electrons which are in turn accelerated by the electric field. By the time the electrons pop out the back of the foil, their speed is relativistic, so they're moving at some significant fraction of the speed of light, so they race away from the surface. That creates, in the jargon, a space charge. So you're separating the electric charge of those electrons you've driven out of the foil from the positive charges which remain. And that potential is then able to suck ions from the surface. So if you've got hydrocarbon type deposits on the surface, the protons from there can be ripped out and accelerated by the space charge which is created by the electrons which are running away. The first observation of this effect was published in Nature in 2006, and I'm just showing you, the data here. People were able to see protons that were popping out of the surface with energies of order of MeV. Of course, people have been developing both lasers, targets, and the target materials since then. And I'm just going to show you the state of the art in a minute. I compiled this slide for reference, so there's a lot of data, a lot of studies out there. I'm only going to pick a few highlights. Let's look at first the Draco laser, which is in Dresden, so the Helmholtz Zentrum Dresden-Rossendorf. So here, there's a 13 joule pulse, which is delivered in a 30 femtosecond time, laser pulse, and has a 3 micron full width half maximum deposit. They do exactly what I described. So the laser impinges on a target. They have a solenoid to capture the particle. So here there's a 19.5 Tesla pulse solenoid. So it's an enormous field. There's a significant technological challenges that come from the ramping of the magnet in a very sharp pulse. So there's a 2 solenoid system where the first solenoid is focusing the beam to a point. There's a collimator, and then there's a second solenoid which delivers the beam to to whatever sample or diagnostic system you want to deliver. So what you're seeing here is a characterization of the beam that was delivered. This is the energy of the beam versus the angle. So you can see that the beam is relatively relatively large. It's highly divergent. So this is plus or minus 20 degrees. And the energies here run from very low energies up to of order 25 MeV. On the right-hand side, you can see the intensity as a function of the Z position, so the distance from the target for two solenoid or a single solenoid system. So you can see the way in which the beam energy is transported. The figure at the bottom, what I wanted to point out was the energy distribution that was delivered by the Draco laser. So they're looking at protons that are impinging on their measurement system in the range 12 to 14 MeV. Okay, and if you look at the beam diameter, they're able to describe that very well, and they're looking at beam diameters in millimeters, which are running from, let's say, 30 to 45 MeV. They've used that to make studies, biological studies. So you see the dose per shot measured in a radiochromic film stack, and they've used markers on tumor models to show you the effect of the radiation. So here's 0 gray on a particular sample, and this is the effect of a radiation with an integrated value of 15.3 MeV, 15.3 gray. In Berkeley, there's a laser, Bella laser, so similar structure. So the laser is impinging on a tape drive, on a thin film target, which is actually running on a tape drive in order to replace the target between shots. Hydrogen, carbon, and oxygen ions are produced from the back of that, and there's an active plasma lens. So this is actually a discharge tube. So it's let's say it's a sister technique to the one that we propose in LhARA. The limitation of this technique is that it's a thin capillary, so the acceptance here is relatively small. However, what they've done is they focus beams using a plasma lens. They've momentum selected in a magnet and directed that to biological samples in a sample holder. So their data, they're looking at the survival fraction of cells, here using the protons they've selected from their target as a function of the dose, and they're comparing that with a reference photon sample. Okay, so laser parameters and other parameters are given on the left-hand side there. Capture is a big issue. There are many, many particles produced, but the only useful particles are those you deliver to the end station. There are various initiatives there. At GSI, there's the Felix laser, and there people are trying to study the capture and the delivery of the beam. There's a system there in which there's a high field solenoid and an RF cavity to limit the spread of the beam in time. And you can see the performance of the beam in the pictures of the experiment at the bottom. So this is the transverse size of the beam at the sample area. So it's about 7 by 7. Sorry, it has this small beam slot size at the target, and you can see, the proton energy and the time distribution that they're able to measure. Okay. I think a system which is very similar to that which we propose is in operation in Beijing. So I think here there's a place where we would love to learn from our colleagues in China. So they have a target system which is very similar to the one that we're developing. They have a quadrupole triplet lens, so this has benefits in terms of simplicity, but has acceptance penalties. And then you can see their instrumentation system, a bending magnet, and then a beam preparation system that takes them to their target. In the bottom, you can see the flux as a function of energy. So they're capturing about around 5 MeV, and they are beginning to do experimentation at that. In Europe, there's of course LhMed in Prague. So this is now beginning, well, it is in operation. It's a system which has permanent magnet quadrupoles to capture the laser, and a momentum selection system, and is really there to study both to develop the beamline techniques and to study the biological and other instrumentation, other effects that are coming from the particles. Okay, so now I'm going to focus on LhARA. So what we have specified, as I said, is a 100 terawatt laser. We want to deliver of order a joule of energy, so 500 millijoules of energy in 35 femtoseconds at 10 hertz. We've specified that because we can buy a laser for a reasonable price. If you consider 1 million currency units a reasonable price, and that will be the start of our beam. A graduate student who's just graduated has performed the most recent simulations of the performance of that device. So in the middle inset, you see the energy versus distance from the source as a contour plot. The particles we're interested in are in the range 15 MeV. So you're looking at the orangey kind of band, and they are really the particles which are coming out quite fast. You can see the after 1 picosecond, the way that they're separated from the target by 60 microns, and they're distributed over a number of microns in space. The energy distribution that came out of the simulation is shown on the right-hand side. We're trying to pick particles from this region here, so in a small window around 15 MeV. And in this simulation and in the data which we've been looking at, the endpoint is a significant distance away. Okay. After the production, we need to capture the particles. The key thing here is to do something which is reproducible, can be done every day, is easy to operate, and we hope is cheap, so that it could be used in many places. And we've focused on what's called a Gabor lens, so it's electron plasma confined in a Penning-Malberg trap. So the key thing here is that the Gabor lenses, which have magnetic fields which are only in the millitesla region and have tens of kilovolts for the confining potential, provide a focusing effect which is as strong as you would get from a 1.4 Tesla solenoid. So we really hope that this is going to be something which is going to reduce cost and floor loading, power supply cost to it. So we hope it's a way forward. We've built a prototype which is shown here in the laboratory at Imperial, and I'm just going to show you the performance. So if you look at the paper that we wrote, we exposed this to 1.4 MeV beams. We were surprised by the results. So this is the beam coming in with the lens being turned off. When we turn the lens on with these different currents in the solenoid, which is confining, which is part of the Penning-Malberg trap, the little dot was turned into a ring, and that was puzzling. So there's definitely an effect. What we found was that there was an instability in the electron plasma, which was known to plasma physicists but not known to us, which is in the jargon called a diachrotron instability. It's really a coherent circular motion of the plasma around the field axis, and the frequency of that is such that you drag the beam, which is injected into the experiment over a period of seconds, around in a circle. And this simulation that was done by another graduate student at Imperial, Titus Daskal, who is able to reproduce the features of the data very well. So we've now embarked on a understanding the plasma before we design a second prototype. So if we do a simulation, either with the performance of a Gabor lens that we hope we can build, or with an equivalent solenoid that we know we can build, we get the beam transport, which is shown here. So this is from H.T. Lau's thesis. You can see using BDSIM or any other code that you would like to have, what the evolution of the size of the beam is. So the beam starts very small and with a very small time structure. It goes through its focusing system. We bring it to a focus to put a collimator, which is selecting the energy. We then transport the beam eventually to a section which prepares the beam for the in vitro biological end station. And we're able to deliver a beam with a spot size that is matched to a standard cell dish. Okay, so we're still working on the optimization of that. The key thing that we want to preserve is the time structure, so we're able to trigger the source, and we want to be able to preserve that triggerability throughout the accelerator chain. So we've chosen the fixed field alternating gradient accelerator technology. That was invented in the 1950s, sort of in a parallel way in Japan and in the US. It's compact and a flexible solution. it allows you to do multiple ion species. You can have variable energy extraction. It has a high repetition rate because you're not ramping the magnets, and a large acceptance because of the way that the magnets are designed. There have been proof of principle studies. For LhARA, we've developed a design which is sketched on the right-hand side. So we have a 10-cell design with a particular magnet construction which allows the beam to radius to increase as the energy increases. We have 2 cavities. We need to change the frequency of the cavities, and we think we want to use magnetic alloy loaded RF cavities of a type which has been prototyped in Japan. And you can see the simulation studies at the bottom. What you're looking at is the transverse, the horizontal and vertical betatron function. So if you like, the size of the beam. And on the right hand side, you're looking at the phase space. So this is the X coordinate. So this is in the plane of the accelerator, and the slope in X. So you can see that the simulation of the phase space gives a reasonable spot size for the beam as it's extracted. I think this is hot news. So last year we submitted a proposal to the UK Research and Innovation Funding Council for their infrastructure fund. And what I'm able to be pleased to tell you is that the first preliminary activity, we were awarded some money, was announced actually last month. So we're now excitedly preparing for October, when we hope to get started on this. Sketches for what we've hoped to be building. I've already shown you the footprint of the accelerator facility itself. Key thing for the first period is the stage 1 design. So this is the layout that we've got in a slightly better than cartoon form that I showed you before, for the laser impinging on the target, the focusing system, and eventually the bend into the first in vitro end station. And of course, we've got a building concept at the bottom there. Okay, so I've lost track of the time. I apologize, Manjit, but here are my conclusions. I started off by trying to advertise that we want to get precision radiotherapy for 2050. In the LhARA activity, we clearly want to develop novel accelerator techniques because we think that it is important to be able to deliver a variety of time and spatial structures of the beam, different ion species and different energies. However, informed by history, but also by a wish to increase the patient throughput through what we hope is a more compact facility, we need to be developing image processing systems, fast feedback and control, real-time dose deposition imaging, and all of those things. So that's the second part of the program. And then I think critical, if we want to have precision healthcare for 2050, we really need to be understanding the fundamental biology a bit better so that the theoretical understanding can be improved to inform the treatment planning software. Inside the program that we're trying to develop, we've got a start on each of these things. So I've shown you, I've really focused on the accelerator because I think that's something which is critical just at the moment. So I've shown you the key things on the accelerator system. There is activity around the image processing, and in particular the dose profile mapping using an ion acoustic technique, and the computing that goes along with that. And we're just beginning to try and improve or work with our biological colleagues to improve the instrumentation of their biological experiments in order to begin to contribute in that area too. Okay, so just to conclude, I believe that laser-driven sources are disruptive technologies and they have the potential to provide a step change in the clinical capability. What we're trying to do is to demonstrate that we can overcome the dose rate limitations of present particle beam facilities by capturing efficiently 15 MeV particles produced in a laser plasma interaction. We want to be able to use that to deliver a uniquely flexible facility where we can vary the ion species, the energy, the dose rate, the time, and the spatial distribution very rapidly. And we want to be able to integrate that in an automated system, which is triggerable. And I think our target really is to reduce the requirement for the large gantry so that we can produce a facility which has a smaller footprint and a lower investment cost than the present facility. The ion therapy research facility, which was what we proposed to UKRI, served by the LhARA Accelerator, which, as you saw from the drawings, is the basis of that proposal, has the potential to prove the laser hybrid systems in operation. And we will be able to, we hope we will be able to contribute to the study of the biophysics of charged particle beams, enhance treatment planning in the short term, I hope, and to create novel capabilities to spin back into science and innovation. So before stopping, I just want to thank my collaborators for all the input to this talk. Thank you very much.
Thank you, Ken. Thanks a lot. So lots to chew on over lunch. So questions from our students, people online, please.
Yes, has a question. Dimitrios, you can ask your question.
Hello, can you hear me?
Hi, yes, loud and clear.
Okay, first of all, congratulations for your presentation. It was very interesting. I would like to ask you, why does the beam hit the full target in 45 degrees and not directly on the target?
I think that's a very good question. I think that we will need to study that to optimize it. So I think if you look at the data, you will find different experiments. People vary the angle, and an optimum appears to be around 45 degrees. So I think that's perhaps not a terribly satisfactory answer. I think there's no, sorry, if you shoot the laser perpendicular to the surface, then the electric fields are actually in the plane of the surface. So maybe that's not the most effective acceleration system. If you shoot at 90 degrees to the surface, then arguably the electric field is now in exactly the right direction to accelerate the electrons, but the laser beam never strikes the target. So somehow 45 degrees feels like a compromise between that, and the measurements seem to indicate that it's a reasonable place to occupy. So apologies. If you had a laser plasma physicist here, he could probably tell you the equations that prove it, but I'm afraid I can't.
Okay, thank you very much.
Okay, I guess while we wait for some other questions, there was actually a very relevant question from the entrance Google Forms. It was more about the future outlook. Simply, can we expect to see the laser hybrid accelerators in the market with clinical applications? And I guess I could add, if so, then what would be your estimates?
For when? Well, so I think that I believe the answer to that question is yes. Otherwise, I suspect I wouldn't be spending all my time on it. I think that realistically, we hope that, or our estimate of the timeline is that over 7 years, if funded in the way that we wish, we should be able to produce a stage 1 beamline. So 7 years from first money. So I think that's probably quite an ambitious timeline, and I guess it depends on how many problems we hit along the way. So if you like, the proof of principle could be done on that kind of timescale. It takes us a bit longer to integrate the fixed field accelerator to boost the energy. But I think that if you ask most accelerator scientists, if you've actually created and focused a beam which is bunched, I think they would be very confident of being able to accelerate that to the energy of your choice. So if you like, the key bit is stage 1. To develop that into a commercial system, that requires quite a number of steps. And our game plan is to develop LhARA in collaboration with industry. I tried to emphasize the system needs, and I think that's where we need to engage with industry. So we have to do the dose profile measurement, for example. We have to be better at doing the image processing. We have to do the automation of the control. And all of those things can be developed in parallel and in principle have application in current facilities to improve the activity. And somehow if you look at the industrialization of it in that way, it doesn't all have to wait till we've got all the technologies working. Probably too long an answer, but I hope it gave an impression.
For that. So don't see any more questions, I suppose. Not nor on Slack, nor in the chat.
So with that, thank you again, Ken.
Thank you.
Thank you for all of you for paying careful attention and being engaged. So I now let you go and have lunch over spatial chat or wherever, however the students are seeing. Christophs, I don't know what you had in mind. And then we see you back at what time? 14:30? I think it's 14:30, isn't it? Yeah, so we'll see you back at 14:30. Bon appetit. Or maybe it's dinner by now, anyway. Okay, thank you. See you later.